My name is Kieran, Lyon. I'm a psychology teacher. I also teach statistics. And what I've been doing in this video series is I've been summarizing, overviewing different psychology books. This week I'm talking about a statistics book, The Lady Tasting Tea, How Statistics Revolutionized Science in the 20th Century. This book was written by David Salzberg. He was a statistician at Pfizer. He was using statistics to develop experiments and then analyze data in order to make effective medications. And you might think, well, this is a book about statistics, it's going to be full of dull, boring equations. There is not a single equation in this book. This book is not about equations, it's about understanding the lives of important statisticians, and it's about finding out about the problems that they had in the real world and how statistics were used to solve real world problems. So it gives a lot of examples. Unfortunately, I won't be able to talk about everyone. I'm just able to give a brief overview. It gives the example of Edward Deming, who used statistics in order to improve quality control to build up Japanese industry. It also gives the example of Pravanta Mahalanobis, who introduced a random sampling to study and then improve the Indian economy. So it gives a lot of examples of how statistics is used to solve problems in the real world. But the big idea of the book is that the statistical mindset, understanding the world in terms of statistics, is actually very new. He's talking about a revolution in the way we think about science, a paradigm shift going from one way to think about the world to another way. So in around the year 1900, people believed in what he calls the clockwork universe, that was mathematical, that was deterministic. He calls it the Newtonian view. I've heard it, he doesn't say that, but I've heard it described as the Newtonian view, which is that, well, Newton derived these short and elegant laws of motion and to explain gravitation. Now, we all know about the scientific impact of Newton, but you don't want to forget about Newton's psychological impact, because the idea was, well, now we can understand this vast, complicated world with some simple and short equations. And so in 1900, about that time, scientists believed that the day was coming soon where we could understand biology and politics and psychology and sociology. All of these things could be reduced down into deterministic equations. That if we knew things, if we knew the predictors, then we could know the outcome with certainty. In the same way that if you know the height and also the base of a triangle, by definition you know the area. The idea was that when the day was soon coming when we could know these things, we could know everything with certainty. We don't believe that anymore. We believe that we can know things with confidence, but not with certainty. So by the year 2000, people didn't really believe in that anymore. Instead, science has been taken over by the statistical idea that the world is complicated and messy. We can know things with confidence, but not with certainty. And Salzberg refers to this as the statistical revolution. He also calls it the Pearsonian revolution, after Karl Pearson. Now, Pearson was one of the first statisticians, well, first modern statisticians, and he was a Victorian man. He was working from the 1890s onwards. And what we knew before then was that we had these equations that would tell us about the movement of the planets and the positions of the moons and so on. But these astronomers would find that these equations would have a little bit of error. And so what happened was that it was a mathematician called Laplace who said, well, we have these equations, but there's going to be some error. The planet will be a little bit this way or a little bit that way, that our laws of physics were a little bit off. But Pearson said, no, it's not that you have the equation plus error. It's that the whole thing can be thought of as error. It's not that we have something certain plus error. It's that the entire phenomenon is complicated and random and can be thought of as a distribution. So here's an example of a distribution. So we have the average of height. And so you can't exactly come up with an equation for height. It doesn't exist. But what you can say is, well, here's the average of height, and there's a lot of reasons why people are shorter and a lot of reasons that people are taller. But what we can do is we can look at the shape of the distribution of height. So in this distribution, this is a bell curve, normal distribution. So how high it is up is the frequency of seeing a particular observation. How far across, in this case, is the height. Most people are average height, but the further you move from the average, the fewer people there are. And so what Pearson was saying is that the real thing of science is not the observation itself. We can't know the observation with certainty, but the real thing that the scientists should be looking at are the probability distributions that we can then use to predict the outcome. I've got this quotation there if you want to read it yourself. And this idea was really taken over all of science. Now, what Pearson was doing, and he had this whole army of statisticians and research assistants who were going around the world measuring things rampantly, measuring the size of different animals and measuring the size of different people and so on, in order to find out these distributions of things. But Pearson made the mistake. He thought that we could actually know the property of a particular distribution. So that's the distribution, and the distribution has a parameter. A parameter is the word that describes the distribution. So he thought we could really know the average height and the average range and the standard deviation of the height. He thought we could actually know these things, but it turns out that we couldn't. Now, this was the next innovation in statistics, which came from Ronald Fisher. He was a very influential statistician who actually wrote a book on the subject called Statistical Methods for Research Workers, which popularized the idea of statistics in research. He was working in the 1920s, 30s, and 40s. And what he was actually doing is he was working in agriculture at the Rothamsted Agricultural Research Station, performing and improving experiments to find out which fertilizers improve different types of food, improve the growth of food. And what Fisher said is, well, we can never actually know the parameters of a distribution, because every time we perform a study, let's imagine we've got 3 different samples of height. I've generated 3 different data sets of 100 different people. I've generated it randomly using the computer program R. You can see that, well, each sample is going to give a slightly different answer, a slightly different mean, a slightly different deviation, and so on. And so we can never actually know the parameter, because every study is going to say something else. And what happens is that what we can do is, as the sample becomes larger and larger, we can become more confident in knowing the actual average height or the actual standard deviation of height. We can become more confident. If our estimates can become more precise, but they're still estimates. We can't know things with certainty. And so he even went further than Pearson. Pearson said we can only know the distribution. Fisher said, no, we can only even estimate that. And Fisher's idea, when you're planning experiments, was that experiments can tell you if things are true or false. But what an experiment needs to do is it works by, you take the data and it needs to be planned in such a way that it's not biased and that it's randomized and that all of your measures are accurate and consistent. But you get the data and then you have to compare it to a statistical model of the world. So this is why the book is called The Lady Tasting Tea. It's named after, in the 1920s, Fisher went to a dinner party with scientists and the families of scientists, and there was a lady there, and she said, you know what? You know when people make tea, sometimes they put the milk in first, or sometimes they put in the water first. And this lady was convinced, I can tell the difference. You give me tea, I'll tell you straight away if it's milk first or water first. Now, and these other scientists were saying, no, chemically they're the same, why would it make a difference? But Fisher, being a statistician, said, okay, well, how about we actually do an experiment, and then we compare the results of the experiment to some distribution. So the idea is, you get the data, you compare it to a distribution. And so what he did is that this lady agreed and had a blindfold on her, and they made lots of different types of tea, with water first or with milk first. He was tasting all of them, and she got every one of them right. Now, so she got all of them right, but let's imagine she didn't. And this is how we get into what's called significance testing, which was originally developed by Pearson, but then expanded by Fisher. So what we can do here is we can imagine, let's say that the lady was just guessing. Let's say that she couldn't actually tell if it was water first or tea first. It would be 50-50, complete guess. And that's what the distribution of this would look like. So sometimes you do the experiment, it would be 50-50. Maybe it would be 51-49, maybe it would be 60-40. It won't always be 50-50. But you can plot that in a distribution, which I've done here. And then let's imagine she got 51 right. Well, that's not very strong evidence that she gets it right, because that's in the middle of the guessing distribution. So that could happen if she was just guessing and didn't know. But let's imagine she actually got something like 62 right. 62% of the trials correct, well then she probably can actually tell the difference here, because what's happening here is that her data, the answers, is at the very far end of the distribution. And so this is called significance testing. And what significance testing says is, given the data, is it unlikely that the distribution is true? And so what we can say here is it's unlikely that she's just guessing. And so what you can do with significance testing is you can take an idea or a hypothesis and throw it away. And you can't actually prove things true, but you can prove them wrong. This idea was formalized by Pearson's son, Egon Pearson, and also by another great statistician by the name of Jerzy Neyman. So this is Neyman-Pearson hypothesis testing. So you have the idea that the drug has no effect, and let's imagine that the medicine doesn't make any effect. And then we'll see, given the data, how unlikely it is that that's true. And then we have this hypothesis that the drug doesn't make any difference. Then we can see if we can throw it out. And they use what's called a p-value for this. And the p-value is the probability that the data actually matches the distribution, that there's no effect. But the problem with the p-value, and in recent years, and the book goes into a lot of detail about the problems with hypothesis testing, in recent years there's been quite a bit of criticism of this, because, well, basically it assumes there's no difference between the two groups, but there always is a difference between the two groups. So the conditions of hypothesis testing aren't actually true. And also you can run the analysis as many times as you'd like to always get a good p-value. And so there's actually some psychological journals that have actually banned p-values. What some psychologists do instead, what statisticians tend to do instead, is use another one of Jerzy Neyman's innovations, which was the confidence interval. So it doesn't make any sense to say that the average height is this with a particular p-value, because you can always get a good p-value by doing enough tests. But it does make a lot of good sense to say, well, we can use a confidence interval margin of error to say 95% of the time we will, if we study height, 95% of our studies will say an average height between this and this. And that means that it's far clearer that we actually have some uncertainty. It doesn't provide false certainty. Now, everything I've told you about before has been about distributions, but since the 1940s onwards, there's been a great deal of innovation in what's called non-parametric statistics, which is statistics that doesn't assume any distribution. It doesn't assume variables are normally distributed. The first one of these was developed by Frank Wilcoxon. It's called a non-parametric test. We don't need to know anything about the actual distribution to find out about the statistics. And in fact, if you study data science, which is a combination of statistics and artificial intelligence, much of that is based on non-parametric tests. And so these kind of tests of normal distributions and hypothesis testing are actually becoming out of fashion. Now, the book's a little bit outdated. Well, it was published in 2001, and that means that it can't talk about the more recent innovations. And one of the great innovations, improvements in statistics, a lot of them being developed by this great data scientist Leo Breeman, is something called machine learning in data science, which is the use of artificial intelligence to create algorithms in order to classify and predict outcomes. So we don't actually need distributions anymore. Instead, we can use far, far larger data sets of millions and millions of people, put it into a computer that runs the analysis in different ways, resampling the data in different ways, thousands or even millions of times, to give us a far more confident and robust result. And, well, you can probably tell that a lot of the book is about the old statistics, because this is the only picture that's actually in color. And so what I'd say about this book is that it's a great place to start if you want to learn about the background of statistics, the ideas of statistics in terms of hypothesis testing, and the problems with hypothesis testing, which is going to be quite a big focus if you're doing, let's say, a research course in psychology or medicine. And as well as that, it's very accessible, although one limitation is that it doesn't cover the more recent research into data science.